Today, we're diving into a really cool breakthrough in how AI learns to connect what it sees with what it says. We're going to be talking about BLIP, a model that figured out how to clean up the messy, chaotic data of the internet all by itself. And trust me, it completely changed the game for vision language AI. So this is the central problem, right? Vision language models have to learn by pairing images with text, and their biggest library is, well, the entire internet. But the web is a wild, messy place. It's full of mismatched descriptions, totally irrelevant alt text, and just noise. So how in the world do you train an AI to see and speak with any kind of clarity when its main textbook is basically a digital junkyard? Before BLIP came along, the field was really stuck on two major problems. You can think of them as these two giant hurdles that were holding AI back from making that next big leap in understanding both vision and language. Okay, first up was what we could call the specialist problem. On one side, you had models like the famous CLIP. Now, CLIP was amazing at understanding. It's what's known as an encoder-only model. So its whole job is to take something complex, like an image, and distill it into a meaningful set of numbers. It could tell you with incredible accuracy if a caption matched an image, but it couldn't write a new caption to save its life. Then on the other side, you had generation models that could write beautiful poetic descriptions, but they often missed the deeper meaning of the image. So researchers had to pick one, a master of understanding or a master of creation. You couldn't really have both.
And so how do we try to make these specialist models better? The strategy was basically brute force. The thinking was, well, if the model isn't smart enough, let's just show it more of the internet. Just drown it in data, and, eventually it'll figure things out.
But here's the massive catch, and the BLIP paper itself puts it perfectly. Web data is, and I'm quoting here, a suboptimal source of supervision. This is the classic garbage in, garbage out problem. It doesn't matter how much data you feed a model. If that data is noisy and low quality, you are always going to limit its potential. And this is where BLIP just completely flips the script. Instead of just demanding more data, BLIP starts asking for better data. It's a huge shift from a brute force mindset to one of intelligent design. This is the absolute core idea. BLIP's biggest innovation isn't just a new architecture, it's a whole new data pipeline. It essentially builds its own high-quality, curated dataset from all that noisy stuff on the web. It's like it makes its own study guides smarter before the real learning even begins. So how on earth does it do this? It's through this really clever two-part process that the creators called captioning and filtering, or CapFilt for short. This is the engine at the very heart of BLIP that bootstraps the data quality up to a whole new level. Let me walk you through how this self-cleaning process works. So imagine you've got an image of a dog, but the caption scraped from the web is totally irrelevant, like "my new camera." First, a part of the model called the captioner looks at the image and just writes a brand new clean caption, something simple like "a dog playing in a park." Then a second component, the filter, comes in. It looks at the image, it looks at the original noisy caption, and it looks at the new synthetic one. It acts like a judge, and it decides which text actually matches the picture, and it just throws out the junk. Only the best, highest quality pairs get to move on to the training phase. Let's break those two roles down a little more. The captioner's job is purely creative. It's a generative model. It looks at an image, and based on everything it's learned, it describes what it sees. Its only goal is to create a plausible, relevant description completely from scratch. The filter, on the other hand, is all about understanding. Its job is to be the quality control gatekeeper. It takes a caption and an image and asks one simple question. Does this text truly accurately describe this image? And if the answer is no, that pair gets tossed out. Simple as that. For any of the developers watching, here's a really simple way to think about it. The captioner is like an enthusiastic junior copywriter, just cranking out tons of content. Some of it's great, some of it not so much. The filter is the seasoned senior editor. Its job isn't to write anything new, but to rigorously review every single piece of text and only give the stamp of approval to what meets the absolute highest standard for quality and accuracy. Okay, so BLIP cleans its own data, which is a huge deal, but that's only half the story. It also solves that specialist problem we talked about earlier by building a single, unified model that can do it all. This is the second major innovation. Instead of needing separate models for different jobs, BLIP uses one single, super flexible architecture, a multimodal mixture of encoder-decoders. The easiest way to think of it is like a Swiss Army knife. An encoder, like the one in CLIP, is fantastic for understanding and compressing information.
A decoder is great for unpacking that information and generating new text. Well, BLIP's architecture can actually switch between these modes. It can act as just an encoder for understanding tasks, just a decoder for generation tasks, or both at the same time for more complex jobs. This unified design is what makes it a true generalist. Now, a new philosophy and a cool new architecture sound great on paper, but does it actually work? Well, the results speak for themselves. BLIP didn't just perform well, it set a new state-of-the-art across a whole range of different tasks. So for image text retrieval, that's a classic understanding task where the model has to find the right image for a piece of text. It saw a 2.7% improvement in average recall. That's a huge deal, and it proved its understanding abilities were even better than the old specialists. Then you look at image captioning, a pure generation task. Here, it boosted the CIDR score, which is a common metric for caption quality, by 2.8%. This proved that the unified model wasn't some kind of compromise. It was truly excellent at both sides of the vision language coin. And even for tasks that need both, like visual question answering, it still set a new benchmark with a 1.6% improvement. I mean, the evidence is crystal clear. The unified, clean data approach is just flat out superior. So what's the lasting impact of BLIP? Well, it's so much more than just a single high-performing model. Its real legacy is a fundamental shift in how we even approach pre-training itself. Really, the biggest lesson from this work is the powerful validation of what we call data-centric AI. BLIP proved that working smarter with your data can be even more impactful than just building a bigger and bigger model. Quality over quantity isn't just a nice little saying, it's a state-of-the-art engineering strategy. And for the researchers in our audience, here's a more technical way to frame this whole process. The CapFilt system closely mirrors a classic machine learning algorithm, expectation maximization, or EM. You can think of the captioner as performing the E step, where it generates expectations of what a good caption should look like. Then, the filter performs the M step, where it maximizes the quality of the dataset by selecting only the pairs that best fit this new, cleaner distribution. Pretty neat, huh? Ultimately, BLIP's influence is massive. It established a totally new baseline for data-centric training. It demonstrated incredible generalization, performing amazingly well on new things like video without any specific video pre-training. And maybe most importantly, it gave all of us a blueprint for how to build models that can learn effectively from the messy, imperfect data of the real world. This leaves us with a pretty fascinating final question to chew on. We started by building systems to just process data. Now we're building systems that actually refine their own learning material. So if an AI can essentially become its own teacher, curating its own curriculum, what does that mean for the future of autonomous learning and for the next giant leap in intelligence? Something to think about.